Yeah, I attempted to do that.
Yeah, I saw.
It didn't work. Yeah. We got one time around, and then it broke off. So I couldn't find the end of the second round. And an error came out. You wouldn't know.
What were you doing? I want you to find this.
Well, first it came out when we were surrendering and I was trying to finish it up. So he got me like where I wasn't doing it. And then I was already full of pie, we had one pie left, and he told me to get the video.
Why would you waste the pie?
I just turned it
Actually, I was reading bills. I was like, hey, these pies are outdated, do you want them?
What?
They were like,
You didn't eat it?
No, he had it thrown in his face. I suffered it.
Well, come back later. I'll give it to you.
it's like,
Unless you have to stay
I
on.
don't know, they're like lemon.
Okay, come back for it. All right. Okay, today, what we're going to do, we're going to take a couple notes today, and then I'll give you some time to work on that. So, that's due when? Tomorrow. Gotta make sure we're going to, I did more than half of those, I'm pretty sure, on the board. So if you've been taking notes, I pretty much did most of them. All right. All right. What we're going to be doing here. We're going to be on section 2.3. There's a couple different topics I need to talk about with 2.3. And what we're going to be basically looking at is the quick way how to graph polynomials. So this is what we're looking at. We're looking at shortcuts for graphing polynomials. Now if you notice, I didn't write quadratics. I wrote polynomials. There's a big difference there. Quadratics, we've already done those. We talked about completing the square, how to find the vertex, how to look at x-intercepts, how to look at a y-intercept, and then you can draw that little bowl. But for a polynomial, these graphs can be anything. It doesn't have to look like a bowl. It can be kind of random in drawing. Okay? So that's what we're going to be talking about today. There's a couple different checks we need to do when we graph a polynomial. I'm going to write the main things that we're going to talk about today. Number one, we're going to talk about the leading coefficient test. That's going to be our first check to see kind of where this thing is going. What it really tells you when you're graphing, it tells you basically what end behavior is. And I'll explain that term a little bit later. Okay, so that's going to be our first check. Second check, what we're going to look at. We're going to look at x-intercepts. Okay, that's what we're going to look at next. Now, x-intercepts is where it hits the x-axis, right? Now, there's this little rule that we're going to do when we check x-intercepts. The rule is called multiplicity. It's called multiplicity. It tells you basically how the x-intercept looks. And I'll explain that more, that concept, what I'm talking about there a little bit later. The third one is actually one of the easiest, y-intercept. Y-intercept. There's no real fancy thing about doing y-intercepts. It's the same structure we've always done. It's the same style of how to solve that from the previous. The next thing we're going to look at, we're going to look at symmetry. So that'll be our third one here. We're going to look at symmetry because that will kind of tell us basically what this graph is going to look like. And what I mean by symmetry, we have that simple test for even versus odd. Even versus odd test. Or I guess we have neither type of symmetry graph. And then the last one we're going to look at today, and these just kind of go all in one problem. They're just quick tests that we do. The last thing we're going to look at is turning points. That's what the textbook calls it. Turning points in a graph. I call it inflection points or oscillation points, where it goes up and down, that type of thing. So that's what the book refers to as. If we can put these 5 tests together, we can get a basic image of what these graphs look like, a real rough sketch. Does that make sense? Kind of what I'm talking about here? Because what we're looking at is like, if I give you just some random equation, can we graph it by hand? That's what I want, without the need of a graphing calculator or even MacBook or Chromebook or whatever you have. Okay? In fact, I'm just going to pick one out of the book and we're going to go through the checks together to see how all these things work. Okay? In fact, I'm going to just pull a problem out of the book here. Let's start with that one. So this is giving me my function, my polynomials. Make sure we're listed down right. Okay, so our goal on this particular problem is to learn how to graph it. See how this thing looks like, where it's going to go, how it's going to interact. Okay, the first thing we talk about is this idea of the leading coefficient, this end behavior of what this thing looks like. Okay, so there's a couple different things we need to talk about. Basically, leading coefficient test. Okay, when we do this test, you are looking at the biggest term on your function. What is the highest degree item we have? X to the third, right? That's my highest degree. This tells us everything about the end caps on this graph. Okay? The number out front is a 1. So that's positive. So that tells us something. And I'll explain that here in a second. The next thing I look at is the actual degree of this thing. That tells us the other thing. That's why in like algebra 2, they always say, hey, find the degree of this polynomial. There's a reason for that. Number one, it tells you how many roots you have, basically how many x-intercepts you potentially have. But it also tells you kind of where the tails go when we graph it. That's why they always want you to find degree. That's just something that they never explain. Okay, so what this means, since it's positive, that means the graph will look like a traditional odd function. Now, what I mean by traditional odd, since it's positive, it's going the normal way an odd function would go, and since it's odd power, odd degree is power of 3, so it's an odd degree. That means the right side is going up, the left side is going down. That's what it means. Right side of this tail, like whatever happens in the middle, whatever is going to happen in the middle, the right side is going to finish going to positive infinity, the left side will finish going to negative infinity. Does that make sense with odd powers? Okay, now if this was negative, that was a negative, like 1x cubed. Then it would just be the complete flip. It would be the odd graph, but it would be going the opposite direction like this. Make sense? Something like that. So that's called end behavior, where the end tails are going. Now, this does not matter if that's a power of 5, power of 7, power of 23. The tails, the outside tails, are following the same rules. Make sense? Okay, so that's easy. Now, the one thing I didn't explain is what happens when it's even. Anyone happen to know if this was an even power, what would happen? Yeah, the tails would go either up or down, right? But they go the same direction. That's the big deal. So if this was like a power of 2 or a power of 4 or a power of 6, the tails would go the same direction on your problem. So there'd be a bunch of stuff that happens, but they go the same way. That's why, like, when we did all those quadratics, our powers were powers of 2s, right? The tails, the outside tails, always went the same direction. They went like both of them went up or both of them went down. But this is an odd graph, so it's going to look something like this on the outside. Okay, questions on my particular problem? Okay, so that's first check. So that's quick. It's like 1 second. Okay, I know where the tails are kind of roughly going. Now that we have that, now we're going to move on to the second check. Okay, x-intercepts. X-intercepts and what they call, quote-unquote, multiplicity. Okay, for x-intercepts, now when we do polynomials like this, we cannot use the quadratic equation anymore. Quadratic equation fails. Quadratics are good for when they have powers of 2s, right? It tells you where you hit your x-intercepts. So when you have a polynomial like this, you have to try to factor it. factor it apart by using all of your factoring skills you get from Algebra 2. Okay, so let's factor this thing apart. So I'm going to put this over here. X cubed plus 2x squared minus x minus 2 equals the y function. All right. So when we factor, how many items are going across? 4. That means we're going to probably have to resort to doing some type of grouping, because it's not a, it's not a cube rule, it's not a difference of squares, it's not trinomial, it's that weird random one. So we're going to try to do it by grouping method. But again, the goal here is to find x-intercepts. So the first thing we have to attempt, if the quadratic formula doesn't work, quadratic equation, the next thing we have to do is we have to factor. We have to factor this thing apart. So these are like the 2 checks that I'm trying. So I'm moving on to factoring. Okay, so let's group things up. So what do these things have in common? Okay, so they have an x squared. Let's take that out. So what's left if I take an x squared from both of these?
X squared.
So x plus 2. Okay, that's the first thing.
Oh, yep.
Okay, and now in the back, what do these 2 things have in common? Negative 1, let's take out a negative 1. So if I take out a negative 1, that's going to be x plus 2. Make sense? Okay. And now at this point, I've noticed like the left side and the right side, they both share something. They both share an x plus 2. So I'm going to take that off of both of these, the left and the right side. So if I take the x plus 2 off, what's left? Squared minus 1. Okay. We good so far with how I factored like the x plus 2 off of both items? Now the left side here, the x squared minus 1, that's a difference of squares. So you got to recognize that these are perfect squares. They're being subtracted, so it's a difference of squares. So that means I got to factor it up even further. So when you do a difference of squares, it's 2 parentheses. It's 2 parentheses. It's going to go plus minus. What's going to be in the front? X's. What's in the back? 1. Okay. So we factor this thing completely. Make sense? Now, to find x-intercepts for when I factor, I set the y over here equal to 0. In fact, let me go over here. So I'm going to set this right side equal to 0. And now I'm reading off what would make each of these parentheses equal 0. Because what's happening here is my y number is actually a 0. That's what I'm doing here. My y number is 0 every single time. So that's going to help us find x-intercepts. That's what I'm doing. So what would make each of these parentheses 0? Negative 1, 1, and negative 2. Okay. Those are my x-intercepts. So that's where my dots are going to be. So negative 1, 1, negative 2. Make sense so far? Now, talking about this idea of what multiplicity is. Okay? What I want you to do is, once we've had this all factored, and if you have parentheses that are the same, you can combine them down. I want you to look at the powers on each of these parentheses. What are the powers on like this first parenthesis? The 1, what's the parenthesis on this, or what's the power on this? 1, and this one? 1. Okay, here's what it says for multiplicity check. Okay, the multiplicity test. If your power is odd, that means the graph will pass through that x-intercept. So it'll pass through that x-intercept right at that spot. So when I start drawing my lines, it'll hit the negative 1, it'll hit the negative, or it'll hit the positive 1, it'll hit the negative 2, and it'll actually pass through the graph at those exact spots. If your power on the parentheses is an even power, and I'll do another one here in a minute where we have an even power for those parentheses. If the power is even. The graph will bounce off of that number. Okay, I'll explain that idea of like what it means to bounce off of a number other than pass through it. Okay, does that make sense? So we're gonna be on this first example, we're passing through each of those numbers because each of those numbers have a power of 1 on those parentheses. Agreed? So now if I go to my graph, I can kind of see what's going to happen here. So we know where the tails need to go. So I know the tail's going down this way. I know the tail's going up that way. So if I can kind of connect the dots here, and I know I got to pass through these points, this is what's happening probably. Since this arrow is going down, right? I'm probably coming up. I'm passing through -2. It's doing something up here, passing through -1, and then coming back through +1 and going up. That's probably what's happening. Because if you look at the test, I had to pass through each of those numbers. I had to pass through -2, -1, and 1 in no particular order. But since my tail over here was negative, so I had to be coming up, passing through the -2 first, and passing through -1 and 1 in that order. They go least to greatest. Does that make sense? Like what I'm doing here? So I gotta like piece it together. Like how does the middle look like it's gonna connect? Now here's the problem. I have no idea how tall those like turning points are. Does that make sense? I have no idea where it's gonna turn. I'm just giving you a rough drawing of what I'm thinking it's looking like right now. So I know at some point it's going to turn again, and come back. So far we found x-intercepts. We, by using multiplicity, I've figured out kind of where I'm passing through it, or I'm bouncing off. We'll do one of those here in a minute. The next check, y-intercept. So this will now narrow down the graph a little bit, where I'm at for the y-intercepts. Y-intercepts are really easy. The y-intercept on this particular problem, this is my y, right? You plug in zeros for all the x's. That's how you find a y-intercept. That you plug x as 0. Okay? So that's my coordinate, right? So if I plug 0, 0 plus 0 minus 0, minus 2. Where am I headed? -2. So that means I'm actually going to hit about right here, and it's probably going back that way. Okay, questions so far? Where I'm hitting the y-intercept? Okay, we're almost done. Almost done here. Symmetry. So I'm going to my problem here. Now I'm going to check symmetry on this particular problem. Okay, symmetry, we have that little check that we did back in chapter 1 to test whether a function is even, odd, or neither. That was on your first chapter test. Here's the chapter 1 test. Alright, so the test for symmetry, if you don't quite remember it, you take your function, whatever your function is, and instead of just having an x in there, I'm going to plug a negative x in all the x locations. This is my check. So right here, I'm taking negative x, cubing it, 2 negative x squared, and negative x, and a minus 2. So I'm plugging in negative x wherever there's an x. Notice I'm not multiplying on it. I'm plugging it in. I'm substituting in a negative x. This, what I'm doing here, this is your symmetry test. The symmetry test is basically, do you know how to substitute correctly? Can you substitute in negative x's correctly? Alright, now what I'm going to do is I'm going to simplify this problem down, and I'm going to take a look at this. Okay, what this thing simplifies into. Okay, so when I have a power of 3, what happens to the negative sign? It's negative. Okay, it's negative, so it's negative x cubed. Okay, it stays negative. What about here? cancels out, right? So it'll stay positive, so positive 2x squared. Negative, negative, positive, and then negative 2. All right, so now, this is my function where we landed, right? After I plugged in the negative x's. Did this turn out to be the same thing that we started with? No, so it's definitely not even. Even functions are when it's the exact same function. What I mean by even, the left and right side are exactly the same picture. Well, I could have told you that. Because do the tails go the same direction? Do they go both up? No, so it's not even. I couldn't tell you that for a second. Not going to be even. Okay? Now, did it turn out to be the exact opposite of what we started with? So like negative, negative, positive, positive. No. So it's not odd either. It's not an odd graph. Odd graphs, the right and left side of the graph look the exact same, right? So it'd be like this. They're like mirror images of each other. Well, it's definitely not that. So this graph is what we call neither or neither, however you want to say it. It has no symmetry. And you can kind of see that. The right and left side of the y-axis, they don't look like the same picture. This side over here starts at negative 2 and goes up. This side went up and then back down. The right and left side of the y-axis do not look the same, so it's not symmetric. Okay, does everyone understand? So this graph does not have any type of symmetry. Okay, the last check here is I'm talking about turning points. Here's how turning points work. And we kind of looked at, how multiplicity works where I'm passing through. This graph, what was your biggest power? 3. The turning points should always be one number less than that. So if your greatest degree is 3, that tells you something about the, the end behavior, right? But it also tells you how many times will it turn directions on the graph. So what is 3 minus 1? 2. That's how many times this thing will turn directions. So I'm going up, I'm going up, I'm going up. It turned directions once. Then it's going down, now it turns directions twice. So it turned directions 2 times. That's the idea. So I can give you an idea of how many times it will oscillate up and down. This thing's going to turn from going up to down to up twice. And that would be your turning points. That just helps me look at the graph. Did I roughly draw it correctly? Yes. So this, what I'm betting on, this is probably what that graph looks like on a graphing calculator. Now, if you want, you can type this in like Google. You can just type in this and hit enter. It'll actually graph.
And you select the highest power minus 1.
Minus 1. Yep. Highest power minus 1. That'll tell you how many times it should potentially turn directions. Nope. You're gonna have to graph it. So they want you to give you a rough sketch. So I'll give you graph paper and stuff. Okay. Does that make sense? Okay. All right, let's try one more. Because I do want to do one where we have something like where the multiplicity bounces. That's all I want to do. So I'm gonna make up a problem. Okay. Make the graph here where we can bounce. So this is my particular problem. Okay, so it's a little bit different. All right, so I'm going to do all these checks. I'm going to go through these one at a time, just like we did, but I'm going to go through a little bit faster. I'm going to try to do this in like 2 minutes, so you can see this. So that way you can see kind of what we can actually look at this. All right, so the first check. Where are the tails going? So, yep, so end behavior. They are going the same direction for my tails. How I know that they're going the same direction? What was my power? Power was 4. That is an even. So that means the tails go the same direction. So in this graph, I'm probably going like this. Or maybe they're both facing down. Now, how do I know if it's going up or down? When you look at your x to the 4th, right? Yeah, the one out front tells you it's going up. So because that's positive, so we're going up. Positive. If it was negative, the arrows would be facing down. We'd be going down to negative. Okay, does that make sense? Okay, so we know somehow the tail's going both up. Let's try to factor this to see where my x-intercepts are going. So we have x to the 4 minus x squared. All right, so we definitely have a difference of squares here, but if you notice, they do have something in common. Let's pull up the common factor first. It makes it a little bit easier to look at. What do these things both have in common? X squared at least. So if we pull out an x squared from both of these, I'll have an x squared up front minus a 1. Make sense? I pull the x squared. And now the right side there, that's a difference of squares, so this can go even further. And this x squared will just go. So this will be plus minus x and x, 1 and 1. And now I know, now I can tell you where my x-intercepts are. So my x-intercepts on this, what would make this thing 0? 0. And that's actually a double root, since it has a power of 2 on it. Okay? This is a negative 1 and a positive. So I'm hitting 0, negative 1, and positive 1. Make sense? Now, looking at the multiplicity, like what we talked about, we have to look at the powers on each of these parentheses here. So, what's the power in this first parenthesis? Second. That means we're going to bounce off of 0. We're going to bounce off it. It's not going to pass through 0. It's going to hit 0 and turn around. Okay? Make sense?
Same with the other two.
Now, the other two. These are 1s. Right? That's the power in those parentheses. So that means we're going to pass through these two. We're going to pass through them. So now I can kind of get a glimpse of how this graph is looking. Since it's a power of 1 on those parentheses, that's an odd number. That means I have to pass through that number. So so if I draw a rough sketch of what this thing looks like, right? Because I know that the tails are going up, right? So the tails are going up. I'm going to pass through negative 1. I'm going to bounce off of 0, and then pass through positive 1. So this is probably what that graph's looking like. It looks like a W in shape. Because I had to pass through negative 1, so I know how to keep going through it. When I turned back to go to 0, I couldn't pass through 0. I had to bounce off it, ricochet off of 0, but then I had to pass through positive 1 again. So it probably looks like some type of W shape. Okay, does that make sense for multiplicity now? Like bouncing versus passing through? Evens, odds for powers. Okay, I already know my x and y intercept. What's my y intercept? 0. I don't need to check. If I put zeros in here, I get a 0 for the y intercept, so that's easy. I can even see it from the graph already. We passed through the origin. All right, let's see. Symmetry. We got to look at this because I think this thing is actually symmetric. So let's check the symmetry test. So here's my function. I'm going to plug in a negative x into this, a negative x to the 4th minus negative x squared. So if I put the negative x to the 4th, that cancels out the negative sign. Put the negative x to the squared, that will cancel out the negative sign. And it turns out to be the exact same thing I started with. So you kind of look at that. So this thing is even symmetric. It's exactly the same graph I started with. That means the right and left side are exactly the same picture. So in fact, my drawing's a little bit off here, but it should be a perfect W. That's what it means. Perfect symmetry. Okay, make sense? How I'm doing that? All right, and we did symmetry turning points. What's your biggest power on this thing? 4. This thing should turn 3 times. It's 4 minus 1. So if we do this, so we're going down here, it turned directions once, twice, 3 times. Yeah, it turned directions 3 times, and that's what graph should do. Okay, make sense? We're going to do a couple more of these tomorrow. In fact, I'm going to have you try some out. So I'm going to put some on the board tomorrow once we go through all of these things again. I'm going to see if you guys can draw rough sketches.
Later on, when you don't have this, the actual coordinates, that way it's...
That's, like how to find where those peaks in memory. Questions? Okay. All right. The rest of the time is yours. You have about 12, 13 minutes here. You can work on page 300. Take your time. It is due tomorrow. Remember, if you owe me any late assignments, those have to be turned in by tomorrow.
Joint term. Looks like the barn prop. The gutter will have a top half. You'll have two sides that are the same, and then whatever's left. Yep. Make sense? Okay. This gutter's bolted on the top.
That's right up there.
And we'll actually do some. No, but
On Sunday though, because I can't do it Wednesdays.
then it's supposed to be right there.
Oh, that's true.
We just put it there.
You can't keep me in your car.
Put toilet paper on it, then turn that toilet paper around.
Oh.
Well, once you put the inside of the body.
They don't do that.
It's everything.
It sounds like this practical joke.
Well, we tried it yesterday.
We used like a huge roll of saran wrap, but it was like really, it was terrible saran wrap.
And then Eric came out and piped it.
Like, I see it coming?
Well, the first time I got held down.
Oh, no.
Well, I brought two pies. First one, it didn't like hit on me, then dropped, nothing like left on me. So the second time I let him record it. It was so much shit in my face. So the first time we go, I had to drop it. What?
I came for like half an hour, not even at the end. I showed up every time for like 10
Hey
minutes
Jack,
at the end.
Matt was there. That was the first time. The whole time? The whole time. He was there before me. Is he gonna keep going? I think so. Better. He's gonna win this first try. He's like, next time we gotta get the frisbee here. Heck yeah. I thought it was kind of frisbee, but it was in like cars. Yeah, but
Yeah, I don't care. I don't
Right, let's get 66. Yeah, 200 feet of fencing being placed right here. So we're going to be closing back. If you're not fenced beside one river, what is it going to do?
Yeah, you're not.
Yes, except for
This is the exact same.
except.
It's the exact same.
Tyler, this one we didn't want to encode that. This one we are encoding it, right?
No, we're not. It's literally word for word the exact same. Read them all. Read them all. It's the exact same. They even stop right at the exact same time.
Well, what are we doing here?
Yeah.
65? Well,
I asked him.
I think we set up right. When we put y equals x.
What do you do with
It's like one of those.
Because, well, we're not enclosing that. We just have 600 feet.
Figure out why it's
And now we just got to find what the maximum.
Don't feel it off.
So like,
say, yeah, if we had to make our own picture, then we have to figure out like 600 minus 2x.
We have to figure all that stuff out.
They did for us. See, that's what I'm doing. Do we subtract one of those from the minus 2x?
You're right, guy.
Now I think Emily's catching on something. Yeah.
Actually,
Theo, what do we do in church? Can you explain that some more? What? What do we actually do?
Yeah, what answer do you need?
No, we had a good lesson yesterday. Oh yeah. Actually, Tyler, when you walked in, I was going out there. We're actually trying to make some stuff.
dude, quit touching her.
Quit talking to the other girl's face.
All right.
I didn't do it.
Slap for no reason. It wasn't that hard, but
Yeah.
$5.
You were not alone.
And then right below it. Cut it.
Probably added the actual was to the original.
Now I
They added these absolute jokes. That's me. That you increased by $5. That makes sense. Because that's on right. Okay, next. Which one?
Brady would like to start.
73. All right. So your factor. So your planes. So every time you take a 15, add.
What's up?
On the other parentheses, you'll have 8,000 passes. Minus. Minus.
Yeah, you sure that's actually
No, we did. No, we did not. Yes. How do we have that answer? 150.
by 300, not by 45.
No, that's the total maximum area.
What's the worst street area?
Yeah, so it was just like that, but 4 had the glass in front of it.
I love it.
9.
9.
And I like it stuff like that.
A little like jump up from
It was like
All of a sudden,
yeah, so and the worst part is my contract is up in the middle.
it's a little
So I sat without a phone. So what I did is I plugged the phone in, so it was charging, and then I just used my iPad. My iPad is synced with calls and texts. So if I had my phone plugged in on Wi-Fi, I can make calls and text from my iPad. So that's what I did. So when I was at school,
what was wrong with your phone?
I shattered mine on the floor. Like it was a day after volleyball. We had our last morning practice, like the first week of school. And I remember walking into the house at 7:30 because I had to come back to school from school. So I was getting changed real quick, and I pulled out my keys and my phone was in the same pocket. And the key like hooked around the phone and pulled it out as I was pulling the keys out. So the phone hobbled from here to the pavement, just shattered both sides of the phone. Because they had the two glass.
Yeah, it's the glass backs.
Yeah, it shattered non-usable. It was cutting the food I picked up. So it's like I plugged it in, let it work, and I was using my iPad to make calls.
That happened to me a long time ago.
was when I, geez, what was that? 6 years ago? And I was waiting for my contract was up in like 3 months. So, and I was like, do I just wait or do I go pay $100? I was like, I'm waiting. I was going to get like 4S anyway.
I knew that.
I remember back in like 7th grade.
John was an expert person who does my test. I didn't get one. No, we have.
I had gotten one
But you think that